this video is on kind of the continuation of this sheet. We're going to be on the back, which is naming ionic compounds. So we just learned how to write formulas, and now we're going to talk about how we name ionic compounds, kind of going the other way. And then the bottom section, which is on something called polyatomic ions, which is a new piece of information. Okay, so how do we name ionic compounds? So this, again, is like the reverse of writing a formula. So, for example, and again, you have on your page, you have the 1, 2, 3 rules and then a practice section. If you would go ahead and copy these 3 practice formulas, we will name them as we go through the rules. Okay. So how do we name ionic compounds? So the first rule is very simple. And the first rule is just that we name the cation as is. Okay. Remember, cation is the positive ion. And in a formula, the positive ion always comes first. So that means this is the cation, this is the cation, and this is the cation. Okay, so we'll go ahead and name these. So all you do is name it exactly as is. So this, of course, is barium. CO is cobalt. And then Al, of course, is aluminum. Okay, so first rule, very simple. We're just naming the cation, okay, or the metal. Just naming the metal. All right, so the second rule is you name the anion and you replace the ending with "ide," okay, or IDE. Which is why we were seeing things like chloride and fluoride before, because the name had been changed. Okay, so we're going to name the anion, which is the second piece in a formula. So in this case, this is oxygen, but I'm going to change its ending to N and ide, so this is going to become oxide. Okay, so this, of course, is chlorine, but I'm not going to call it chlorine. I'm going to call it chloride, and I'm just writing it underneath because I ran out of space, okay? And then, of course, over on the third example, that's also oxygen, which, of course, will be oxide. So naming is pretty simple, and then there's a third rule, which only applies sometimes, and that third rule happens if there's a transition metal. Okay, so the third rule says only if there's a transition metal. We have to indicate its charge using a Roman numeral. Now, remember your transition metals? Here, I'll try to draw you the chart. Okay, and you have a line, right, that goes like, wherever it goes. Okay, your transition metals are kind of all here. Okay, pretty much. So, we're only looking for the ones that have a transition metal. So, is barium a transition metal? No. Barium's a regular metal, so we're done. Is cobalt a transition metal? Yes. Okay, so we'll come back to this one. We're going to have to deal with this. And then is aluminum a transition metal? Aluminum is not, because I know that aluminum is +3. So I don't have to deal with that on that one. So the only one I have to deal with is cobalt. So this sometimes is confusing for students, but I try to make it simple by suggesting that you draw a picture. What I mean by that is, if my formula here is CoCl2, doesn't that mean that I have 1 cobalt and 2 chlorines, right? I have to, based on my formula. My formula tells me I have 1 cobalt and I have 2 chlorines. So that's what I have drawn as my picture. I know chlorine's charge. It's -1 and -1. Okay, so the question here is, what does cobalt's charge? Remember, there's only one of them, right? what does cobalt's charge have to be? Well, we know it's a positive, so that it cancels out with these two negatives. And of course, that answer is, it's got to be a positive 2. So this is cobalt 2 chloride, which means I have to tell my reader that this is cobalt 2 chloride. Okay, and you can either do your Roman numerals like that, or you can cross them, doesn't matter. Okay, but this name is not complete until I tell the reader of the name in my formula that it has a charge. Okay, I didn't have to do that here with barium because we know barium's charge is +2, right? Barium's right here. And it can never be anything different. But cobalt is a transition metal, and cobalt's charge can change depending on its formula. So if it's a transition metal, you have to think about that, and we have to keep that in mind. One other thing I wanted to say, or draw your attention to, is if you look at this name, aluminum oxide, okay, the name aluminum oxide tells you nothing about the fact that there are 2 aluminums and 3 oxygens. Okay, so that sometimes is also misleading for students, because the name of something really doesn't tell you how many there are. If you think back to what we just learned, you have to equal out their charges to write a formula. Okay, so a little bit different. All right, so there are 6 practice questions, or naming questions. So I'm going to erase this and then go ahead and give those answers. If you would like to pause this video and try those 6 on your own, it'd be a good practice. Okay, I'm just going to go right in, but if you wanted to, if you still need to pause, you're welcome to. Okay, so here we go. Naming these things. So, first one, that's sodium iodide, right? Don't forget, you gotta change the name. Sodium iodide, and sodium is not a transition metal, and so that's it. This thing is sodium iodide. Done. Number 2 is potassium nitride, okay, not nitrogen, nitride, and potassium is not a transition metal, so I don't need anything else, and I'm done. My third one, SnF2, that's tin, okay, and this is fluoride, but tin is a transition metal, so this is one of those ones that you're going to want to think about. So I have 1 tin, I have 2 fluorines, based on my formula. Fluorine is -1. Tin has to be +2. So this is tin 2 fluoride. Number 4, this is copper. Copper is a transition metal, so I know I'm going to need this. Chloride, again, with my picture, I have 1 copper and 2 chlorines. Chlorines -1, -1. Copper's got to be a +2. Oops, sorry. So this is copper 2 chloride. Number 5, SrCl2, that's strontium. Strontium is not a transition metal, so this is just strontium chloride. And number 6 is potassium sulfide. And potassium is also not a transition metal, so I'm done. And that is naming ionic compounds. Okay, so basically in naming, the only thing you have to watch out for is changing the ending to "ide" and watching out for those transition metals. Okay, so we're going to do the bottom of this paper. But before we do the bottom of this paper, you need to make sure that you have this paper. And this is called, this is the periodic table of ions. Okay, so a couple things about this. So first of all, ions we know have charges. So if you look at all these boxes, they all have charges. Okay, you'll notice that your first 2 groups are missing, and then all these guys over here are missing. Okay, And that's because there's no need for us to discuss their charges. We know what they are. +1, +2, +3, -3, -2, -1. Okay, they're the ones that follow the pattern. The ones who are on here are your transition metals. And they're showing you that some of them can kind of flip-flop, okay, and be numerous charges. Now, this is not an all intensive list. So, for example, if you look, this says that iron can be +3. Is this focusing? Not really. It's saying that iron can be +3 or +2. Iron can also be +6. Okay, there's other charges that these things could be. So keep that in mind. And I do want to draw your attention to two of them in particular. And so you might want to highlight or mark on your paper that silver, okay, silver Ag, silver is always ever only +1. And zinc is always only +2. Okay, so those are important. Now, the bigger piece of information from this table is this upper part. Okay, and if you can read it, it says the table of polyatomic ions. So you don't need to write this. I just want to have a small little lesson. So what we have been discussing so far are things called monatomic ions, and mono means one. Okay, so a monatomic ion is like chlorine -1, sodium +1, O -2. Okay, they're all single things. What we're now going to talk about are polyatomic ions. And of course, poly means more than one. So if you look at this chart of polyatomic ions, you see that some of them are pretty complicated. Okay? So what's a polyatomic ion? So if you look, probably the simplest one is the polyatomic ion whose name is, where'd it go? Hydroxide. Okay? So if you look on your paper, hydroxide is OH with a charge of, your paper says minus, which means -1. Okay, and so technically what that means is it's a oxygen and a hydrogen stuck together, and the whole thing has a -1 charge. I mean, we could draw a Lewis structure for this, right? We drew Lewis structures before. But the point is that it's just more than one thing stuck together, unlike like this, for example. Then they get a little more complicated, then you have like nitrate. Okay, if you look up nitrate is NO3 -1. So meaning 1 nitrogen, 3 oxygens, the whole group has a charge of -1. And then they get real complicated. And actually, if you look at your paper, it's the first one, acetate, okay? And if you see acetate, it's written like this. CH3COO, that whole thing has a -1 charge. Okay, it's at the very top of your paper right here. I would also like you to add, and you can just write it right above, that acetate can be written another way. And it can also be written like this. Okay, and if you think about it for a minute, C2, 1, 2, H3O2, it's the same thing. Okay, it can just be written two different ways, and so that is helpful to keep in mind. Now, how do we deal with polyatomics when we do formula writing? Okay, it's exactly the same stuff we've been doing. Charges have to equal out to 0. Okay, so it's not really a whole lot of new information. So if you go back to your sheet, we're on the bottom, and it says compounds with polyatomic ions. The same rules apply as when we write regular formulas. And then it says 2 examples: calcium carbonate and magnesium hydroxide. Okay, so same rules apply. So calcium's charge is +2. Now carbonate is a polyatomic. Okay, carbonate is, wrong paper, sorry. Carbonate is a polyatomic ion, and we look him up. There he is. Carbonate is CO3 with a charge of -2. Okay, same rules apply. We look at +2 and -2, they add to 0. So all I do is think, how many calciums do I have? 1. How many groups of CO3 do I have? 1. Now, sometimes students like to drop this off. I'm not allowed to do that. Okay, it's part of my formula. And this is the formula for calcium carbonate. Same rules, okay? The only time we get into something slightly different is in this example. Magnesium hydroxide. So Mg plus 2. Hydroxide, that's the one I gave you as an example a minute ago, is OH with a charge of -1. So they're not equal. So I need a second OH. -1 plus 2, I'm good to go. When I go to write my formula, though, something happens. So if I say I have 1 Mg and I have 2 groups of OH, a lot of students do this, but you run into a problem. And if you think about it, the way that's written shows me that I have 2 H's, but only 1 oxygen, and I have 2. Okay, so the issue with a polyatomic is if I have more than 1, 2, what I'm going to do is put the polyatomic in parentheses and then put my subscript. Because then it becomes like the distributive property in math class, that the 2 not only applies to the H, but the 2 also applies to the oxygen. And so this is my formula for magnesium hydroxide. You might be questioning why I didn't need parentheses over here. Well, I only had 1. So, I mean, you can, it'll make you feel better, but it's not really how it's done in a textbook. Okay, so only if there's more than 1 polyatomic do you need parentheses. So there's a couple practice. Let's go through those real quick. Or you can try again. You're always welcome to try. Pause the video and then check my answers. Some of these are easier than others, and it just takes some time to get used to these. I'm going to run out of room here. Sorry. Potassium phosphate. So again, the important thing to know is that all the same rules apply. Charges have to add up to 0. You do that by adding more of something. And then you write a formula. Okay, so here we go. Sodium hydroxide. Sodium's charge is +1. Hydroxide, we've seen several times today, is -1, +1, -1. Good to go. Squish them together. NaOH. Sodium hydroxide. Done. Second one, ammonium hydroxide. Ammonium sends students on quite the hunt, but here's a hint. It's a positive polyatomic ion, and it's hiding right there. Ammonium is NH4 +1. Hydroxide, of course, is OH -1. This example is actually made of 2 polyatomics, but I'm going to treat it no different. I have a +1 and a -1. I'm good to go. So my formula, NH4OH. Third example, lithium carbonate. Lithium's +1. Carbonate is on my chart, on my polyatomic, and it is CO3 -2. Okay, I have a +1 and a -2. I need an extra lithium. So my formula is lithium 2 CO3. Not allowed to get rid of that 3. It's part of the formula. Li2CO3. Potassium phosphate. Potassium's +1. Phosphate is PO4 -3. Means I need some more potassiums. Formula is K3PO4. Notice none of my formulas have charges in them, right? Because the charge is 0. Magnesium nitrate, Mg +2. Nitrate is NO3 -1. I need one more nitrate. I have 1 Mg. I have 2 nitrates, right? But the way you're going to show that is put this in parentheses and put a 2. That's the tricky one. And then last, potassium sulfate. Potassium is K +1. Sulfate is SO4 -2 from your sheet, right? Not sulfide, that's sulfur. Sulfate. I need an extra K. K2, SO4. And there it is.